All right, hello everyone. Welcome to class 15 of this course. So, just to recap what we have been doing, we have started the idea of what is called a point group in the last class, but before that we were trying to look at what a Bravais lattice is, what lattice I mean. So in general, where does the translational symmetry come in the form of lattice, right? So, lattice is a construct through which we can put in translational symmetry. The Bravais lattice, description of a Bravais lattice, and all the crystal systems, but the crystal systems themselves are defined based on the underlying symmetry that exists in at several points in the lattice, right. So, a good way of actually describing these symmetry operations actually come in groups, right. So I am just not, if there is a certain operation, there is bound to be a certain other operation about a point, and these points are called point groups. We have formally defined what a point group is earlier. So mathematically a group, if P and Q are operations of a group, then P times Q is also an operation of the group. And then group should have the identity operation, it should have an inversion operation, and also it should be include the associativity, right. So, based on that, mathematically we say something is a group, but from the point of symmetry operations we have set of symmetry operations that come in, and then they are grouped together as what is called a point group. Okay. So, with that background, let us go into the development of, we said there are 32 different point groups in a crystal, which means that these 32 different point groups are actually compatible with the translational symmetry that exists in a crystal, right. So, in a crystal, if we have to develop each of these point groups systematically, let us go back to the idea of so what every crystal system, and then let us see what are the symmetry operations that could exist in a crystal system, and let us try to list them out. Okay. So we are going to do that exercise right now. To develop point groups, let us start with a triclinic system. And we said the only kind of operations that could exist in a triclinic system are 1 and 1 bar, right. So, if I have an operation 1, which is just the identity operation, so it is just one operation, right. So, there is nothing, if I have an operation 1, it is not, so that is if I rotate a point by 360 degrees and then it comes back to its own position, it's trivial symmetry, it's an identity operation. And in the identity operation, so if I am going to define it as a group, the only point group operation in this identity operation 1 is the only point group operation in the the only operation in the point group 1 is the identity operation 1. So, here it becomes a bit confusing, because so this I am defining it as a group, and this is the element of a group, right. This is my P operation or Q operation, right. So, the only operation I have in my group is identity operation, right. So, which is 1, right, in the notation that I am going to use. So, so that becomes very trivial. The number of elements of the group I am going to define it as H. H is the number of elements of the group, and the number of elements of the group in so in a triclinic system is just 1. Okay. In a triclinic system with which just has the identity operation as the symmetry operation, right. So, now if you look at 1 bar, however, right. So, 1 bar would include, if 1 bar were a point group, right, what are the set of operations that that dictate this group, that are present in this group, and the set of operations are actually 1 and 1 bar, right. So, 1 bar is the inversion operation and 1 is the identity operation. We said every point group, every group should have an identity operation, right. So, so 1 and 1 bar are the identity are the identity operation. 1 is the identity operation and 1 bar is the inversion operation. So, in this point group I have 1 and 1 bar. So, the H of this, or the number of elements in this point group is actually 2. Okay. So, so that's a simple description of triclinic system. If I can have can I have any other symmetry operations in a triclinic system? The answer is no. The next highest symmetry I go to is twofold rotation, and if I have at least one axis with twofold rotation, I am going away from triclinic system and I am going into what is called a monoclinic system, right. So, monoclinic crystal system. So, in a triclinic system, maximum I can have is 1 bar, right. So, 1 bar is the maximum symmetry point group. So, 1 bar or the inversion, right. So, point group is the maximum symmetry, is point group with maximum number of symmetry elements in it, let us put it that way. Okay. And the in a given crystal system, the group that has maximum number of symmetry elements is what is called a holohedral point group. Okay, this is just a definition, holohedral point group. Okay. So, then alternately, if I ask you the question, what is the holohedral point group of 1 bar of triclinic system? I am going to say that is 1 bar as a point group, right. 1 bar consists of two different operations, h equal to 1 and h equal to 1 bar, two different operations, h equal to 2, and these two operations are 1 and 1 bar. Okay. So, it's a bit trivial right now. I am using the same notation, 1 for an operation, 1 also as a group, right. It becomes clearer when we go to a more sort of monoclinic system, right. Now, let us go to monoclinic system. A monoclinic crystal system has certain points about which I can have a twofold axis of symmetry. Okay. Only one axis about which I can have twofold axis of symmetry, right. So, I am going to let us say that axis is the C axis, or 0 0 1 is the axis about which there is twofold axis, twofold rotation, symmetry. So, what are the other operations? So, I am going to describe this point group where I only have one twofold axis of symmetry as let us say 1 1 2, and 1 1 2 meaning so the only operation about A axis, this is A axis, this is B axis, this is the C axis. The only operation about the A axis is a one-fold operation. The only axis about a B axis is twofold rotation, and the only axis about the operation about C axis can be one-fold or twofold, right. So, rotation. So, this is so this, instead of writing 1 1 2, I am just going to represent it as point group 2, right. And by 2, the elements in 2 are actually identity, and I have a twofold axis of rotation about 0 0 1. Okay. So, I have a one-fold axis of rotation, and I have about any axis ideally, and I have twofold axis of rotation about 0 0 1, right. So, these are h equal to 2. Okay. And if I may go back, actually let me correct it here. It is for something to be defined as a group, because here I am actually defining something like 1 and 2 as groups, and they do not really have the inversion operation in them, right. So, yeah. So, I may want to clarify here that the inverse should exist, that is, if P is an operator, P inverse should be an operator, but inversion operator does not need to exist. Inversion operator is a 1 bar operator, right. So, in a group it is not necessary that a group consists of an inversion operator, right. Now, what is the inverse of operation 1? It is 1 itself, right. So, because I apply 1 and 1, I get 1, right. So, so an inverse of every operation should exist inside a group, but the inversion operation need not exist. Okay, so that is the clarification. So don't get confused, right. So identity should exist, and so if I have a two-fold operation about 0 0 1. So how am I going to represent that? So I can represent it as what is called a stereogram, right. So we did this earlier. So a two-fold operation about 0 0 1, right. So I can actually, if I have an asymmetric point here, the same asymmetric point should exist here at an angle of 180 degrees, right. Now I could either go this way or this way. These two are inverse operations of each other, right. So both of them exist, right. So I can go either clockwise or anti-clockwise, it does not matter. If I go clockwise, I should also be able to go anti-clockwise, right. So both of these are identical operations in this case, right. So 2 or 2 inverse is the same. But so the inverse does exist in this group. Okay. So, but overall, if I am just counting the number of operations in this group, so 2 has one two-fold axis of symmetry about 0 0 1, and the rest of them are all trivial identity operations. Okay. So I am just going to represent it as 2. Okay. Okay. Now what else I can have? Can I have two-fold axis of symmetry? No, because if I have two-fold axis of symmetry, I am going to change the crystal system, right. So the crystal system then becomes an orthorhombic crystal system. Rather, I can just have 2 bar or mirror, right. So mirror about 0 0 1, let us say. Okay. So so I can the point group, I can exactly write it as 1 1 m or just m. In simpler notations, I can just write it as m, right, and m would consist of again an identity and an m, right. So there are 2 different h, or the number of elements in this group are 2, right. So I have an identity and I have a mirror. Okay. So a 2 and an m, right. So what are the different point groups that we have listed so far? In a monoclinic system, I have listed 2 as a point group, I have listed m as a point group, right. Now, can I combine these 2 in a certain way such that I get another so I can have operations that combine both two-fold axis and a mirror and still retain the monoclinic symmetry, right. Is that possible? Indeed, that is possible. I can have another operator where I just have one fold axis of symmetry, right. Now if I so I have 3 axes, right. So for example, I can make A axis is just one fold axis of symmetry. If B axis is m and C axis is 2, first of all, this such a group will not exist, right. So I should have another m by if I have m about B axis and 2 fold about C axis, I should have another m, and so if I am having 2 m's, or I should have another 2 fold axis, not an m, sorry. So it's a 2 m sort of thing. But if I have 2 fold axis of symmetry, then I am not in monoclinic system anymore, right. So I cannot have a mirror which is actually parallel, or so the normal to the mirror cannot be perpendicular to the 2 fold axis, right. So the only thing that is possible is 1 1 and 2 by m, right. And what do I mean by 2 by m? 2 by m means I have a 2 fold axis of symmetry and I am cutting it with a perpendicular mirror, right. So my 2 fold axis is about 0 0 1 and my mirror is also about 0 0 1, or the normal to the mirror is exactly parallel to 0 0 1, right. So my 0 0 1 axis has a mirror which cuts perpendicular to it, and the 0 0 1 axis is also a 2 fold axis of symmetry, right. So it is both, it has a mirror component as well as a 2 fold axis of symmetry. Okay. Now if we look at such an operator, right, what are the different operations that come up? Okay. So if I have one axis, the C axis, about which I have both 2 fold axis of symmetry, and about a point along the C axis I have a perpendicular mirror which is perpendicular to the C axis. Okay. So of course so I am just going to represent this as 2 by m. Now it is here in this convention I am saying that is the C axis, but I can have a 2 fold and an m and a perpendicular mirror either along A axis or B axis, but only along one axis, not along 2 axes, right. Okay. So 2 by m, so it should have an identity, of course. It has a 2 fold axis about 0 0 1, that is the second operation. The third operation is it has a mirror about 0 0 1, but there is something else, a hidden operator, a hidden in symmetry operation that I am not seeing here, and what is that, right. So, a twofold operation about 0 0 1, what does it do? It takes my point x y z, right, to minus x minus y, but the z remains, right. So, the matrix of transformation is just minus 1 1 0 0 0 0 0 0, whereas a mirror about 0 0 1 does exactly the opposite thing. If I have x y z, right, sorry, let us do it properly. If I have x y z with chirality, with a positive chirality, and this is out of the plane. So, I will have one that goes in the plane and one that is out of the plane. Sorry, how did I represent this? So, yeah, so there are going to be two different things. There is going to be something that comes out of plane, something that goes in plane, and the chirality also changes. So, it changes from so you have both right handed as well as a left handed system. Okay. So, essentially the point x y z in this case, right. So, in case of a mirror, the point x y z is transforming into a point x y minus z, right. That is the perpendicular mirror, and the perpendicular mirror is represented as in the stereograms. I am just going to shade this, right. So, this circle will be let me see if there is a shading option here. There is a highlighter, and I am just going to use the same color and highlight this, right. So, okay, so if I draw a thicker circle, that means I have a mirror which is perpendicular to the plane, right. So, if there is a mirror that is perpendicular to the plane, whatever I have, if I have a right hand here, I will have a left hand just below the plane. Okay. So, all right. So, the operator that changes this, the symmetry operation, the matrix that describes the symmetry operation is 1 1 minus 1 0 0 0 0 0. Okay. So, this is the operation P, this is the operation Q. So, if P and Q both of them are operations in my group, in my point group, then P times Q also should belong to 2 by m, which is my point group. Now, if I do P times Q, what do I get? I get PQ is an operator which is just minus 1 minus 1 minus 1 0 0 0 0 0 0. Okay. So, that is nothing but that is an inversion operation, that is 1 bar operation, right. So, if I have a mirror that hits my twofold axis of symmetry, by just by having these two operations, what comes for free is the inversion operation, right. So, these materials with 2 by m sort of symmetry also are centrosymmetric, which means the other operator that I have to write here is actually the 1 bar operator, right. So, I also have an inversion symmetry that comes for free, right, just because I am putting a twofold axis and cutting it with a perpendicular mirror. And you can see that this is the case with almost any form of rotations, any form of so combinations of rotation and mirror. If I have an axis, if I have a fourfold axis of symmetry and I cut it with a perpendicular mirror, I get an inversion, right. Inversion comes for free. So, if I have a sixfold axis of symmetry and I cut it with a perpendicular mirror, anything with n by m sort of a point group, right, or if n by m exists in your point group, then I can close my eyes and say that that system has inversion symmetry in it. Okay, but this should be a perpendicular mirror. So, how do I represent a perpendicular mirror? Along c axis, if there is an n-fold axis of rotation, I am going to write n by m, right. So, both n and m are about the c axis. Okay. So, that is the notation. Okay. So, okay. So, how do I represent 2 by m? So, I have I have so I am just going to not represent chirality anymore in these stereograms. So, I am going to say that okay, so I have a circle that goes inside the plane, a dot that comes outside the plane, right. Now, if it is mirrored, the chirality exchanges of course, but I am not going to represent chirality from here on because it just gets more and more complicated. If I put the commas and pluses and minuses, it just becomes more complicated, right. So let us reduce the number of things that I use to represent an asymmetric unit, and this is how I am going to represent an asymmetric unit. Because there is a mirror, so if I have an asymmetric unit above the plane, there should be an asymmetric unit below the plane, but again the chirality comes, right. So it's the mirror image. If I have right hand above the plane, I will have left hand below the plane, but I also have a two-fold axis of symmetry. So again the same thing gets repeated here, right. So this is how a 2 by m, and I have a two-fold axis of symmetry which is this, and I have a mirror, and mirror I am just going to shade this thing, right, which is like this. Okay. Now very soon we are just going to separate these into two different entities, right. So these are what are called stereograms or stereographic projections or stereographic representations. It becomes clear that this is a real stereogram when we go to cubic systems, but before that, so just take my word that these are what are called stereographic projections. Okay. So I am going to split them as, so one just to represent the asymmetric units, right. So I have asymmetric unit here and here, and the other one to represent just the symmetry elements, right. So I am not going to represent, so this stereogram I am just going to represent the asymmetric units, right. This is the stereogram with asymmetric units. Okay. And I am also going to tell you the stereogram which says that I have a two-fold axis of symmetry. This is my two-fold axis of symmetry, and in addition I have a mirror, right. That is it. So now this will tell me what are all the different operations I have. I have a two-fold axis of symmetry, and I have a mirror that cuts across the two-fold axis, that cuts perpendicular to the c axis, right. So that tells me that what I am looking at is a point group 2 by m, and so if I want to see how the asymmetric units are represented or where all should they be, then I look at the figure that shows me the stereogram that shows me the asymmetric units, right. So this just represents the symmetry operations. There is one two-fold axis and one mirror. Okay. So that's the that's how we interpret these sort of stereograms. Okay. So now can I have anything else in monoclinic system? So I had 1 1 2, right. I had 1 1 m. I had 1 1 2 by m. I combined both two-fold axis of symmetry as well as mirror. Can I have something else? The option is, I cannot have anything more than two-fold axis of symmetry, then it is no longer a monoclinic system. But at the same time, I cannot have at least two orthogonal axes having two-fold or mirrors, right. So that is also not going to be a monoclinic system. So these are the only set of point groups, Each of them is a group, right. So these are set of point groups in a monoclinic system. Crystal system. Okay. Now, what is the holohedral point group? Of a monoclinic system? It is 2 by m. Right. So 2 by m has both identity, inversion, two-fold and a mirror, right. So h equal to 4, highest number of symmetry operations that I have in 2 by m. So 2 by m is the holohedral point group. Now people may ask you questions like, what is more symmetric? I have a crystal which has just a two-fold axis of symmetry, right, and I have a crystal which has a point group 2 by m, right. 2 by m is not about an axis, it is about a point. You have unique points, right. So because I take an axis and then I cut it, right. So that point becomes unique, right. So I take an axis and then I cut it with a mirror, right. So, the intersection between the mirror and the axis becomes a unique point, right. So, about that point I have a 2 by m point group, or I have an inversion, I have so all these things. Whereas twofold is not, I mean, so it's an axial, I mean, so we'll come to it. It's called a polar group in some sense, because there is no unique point along the twofold axis of symmetry, but that's okay. So, so I give you a crystal with that which has an underlying point group which is 2 and an underlying point group which is 2 by m, and I ask you the question which is more symmetric, right. So, somehow intuitively you tell me that 2 by m is more symmetric. But if I have to ask you what exactly defines more symmetry or less symmetry, it is this h value, right. So, the number of symmetry elements in the point group. Okay. So, so that defines whether I have more symmetry or less symmetric crystals, right. So, that is the so you can formally define higher symmetry and lower symmetry just by the number of symmetry operations in a point group. Okay. All right. So, that is the monoclinic system. Next, in the laundry list of things, we will go to what is called the orthorhombic system, right. Okay. Now, an orthorhombic system is, we said you need to have at least 2 orthogonal twofold axes of symmetry, or 2 orthogonal mirrors, right, or some sort of combination of them, right. So, it can just be 1 twofold axis of symmetry. So, that's good then. So, I have a twofold axis of symmetry about 0 0 1, and I have a twofold axis of symmetry about 0 1 0. Okay. So, this is the matrix of transformation here is x and y become -1, z remains as it is 0 0 0 0 0. This is my P. Q is minus 1 1 minus 1 0 0 0 0 0 0, right. So, these are the 2 operations that I should have in my crystal. So, if I have both P and Q, PQ should belong to the point group. Now, what is PQ? R equal to PQ, and that will be so the one changes its position -1 0 0 0 0 0 0. Okay, and that is nothing but a twofold axis of rotation about 1 0 0. Okay. So, if I have 2 twofold axes of rotations which are orthogonal to each other in an orthorhombic system, and that gives you that so my axes are actually going to be perpendicular to each other, that tells you that what I have is an orthorhombic system, then I should just because these 2 operations exist, the third operation also should exist, and that is a twofold axis about 1 0 0. Okay. So, the first point group in the orthorhombic system hence is going to be 2 2 2, right. Now, 2 2 2 means twofold axis about A axis, twofold axis about B axis, and twofold axis about C axis, right. Now, what are the elements in 2 2 2? I of course have an identity. I have twofold about 0 1 0, I have twofold about 1 0 0, I have twofold about 0 0 1. Okay. And accidentally does something else come up, it turns out that it does not come up. So, H is actually equal to 4. Okay. All right. So, that is good, but I also can have 2 mirrors, let us say, right. So, we said instead of 2 I can also go to 2 bar, or 2 bar is the same exactly as a mirror, right. So, if I have m and m, right. So, m about again 0 0 1 and m about 0 1 0, you can show for yourself, I think we already did this, that what comes for free is a twofold axis of symmetry about 1 0 0, right. So, 2 mm is my second point group. So, let us count this. So, this is the first point group in the orthorhombic system, this is my second point group in the orthorhombic system, and again what I have are 1 twofold axis about 1 0 0, m about 0 1 0, and m which is also perpendicular to 0 0 1. Okay. So, if I have 2 mirrors, right, so I get a twofold axis for free, an orthogonal twofold axis for free, right. So, this is the second point group. Now, you know, so depending on the convention or notation, you know, so I can have MM2 or M2M or 2MM, all these are, you know, you just these are, you know, so just you coordinate transform. So, you know, A becomes B, B becomes C, and so on and so forth, right. So, so different people use different notations. So one can use MM2, one can use 2MM, but these are all different settings of the same crystal, right. So these are all different settings of the same crystal. Okay. So let us then try something else, another combination, right, and this other combination is going to be, so I tried 2mm and I tried 2 to 2. So instead of 2 mirrors, now I will have two two-fold axis of symmetry, right, and I will have a third mirror, okay, so which is perpendicular to this, right. Now let us see what this actually gives. Does it give some extra elements? Okay, so if I have two perpendicular two-fold axis of symmetry, what I will also have is a third two-fold axis of symmetry. So what I will have is 2 by m. Okay. Now you can also show that if I have a two-fold axis of symmetry, which is, you know, about the b axis, which is minus 1 1 minus 1 0 0 0 0 0 0. This is a two-fold axis of symmetry about 0 1 0, okay, and I have a mirror about the z axis, which is 0 0 1, and that will be, you know, written as 1 1 minus 1 0 0 0 0 0 0. So these are the two operations that I consider. This is P and this is Q, and I just look at what PQ is, right. So based on the property of the group, what should I get PQ to be? PQ is just going to be, you know, minus 1 1 1 0 0 0 0 0 0. So this is nothing but a mirror about 1 0 0, right. So mirror perpendicular to the 1 0 0 rather. When I say about, in case of mirrors, what I am looking at is the normal vector to that mirror, or in other words, if you take the 1 0 0 axis and then cut it with a perpendicular mirror, that is the mirror that I am talking about. Okay. So, so it is one and the same, right. Okay. So then, you know, so by since I had two two-fold axis of symmetry, I got a third two-fold axis of symmetry, but I already have a mirror. But since by virtue of having a two-fold axis and a mirror here, I get a mirror, another mirror along the A axis, right. And then I can take any other combination. I have a mirror here, I take this and this two-fold axis of symmetry, then I get another mirror here, right. So this becomes a point group. So if I have two two-fold axis of symmetry and then one mirror, what I get for free are the other mirrors, which are other orthogonal perpendicular mirrors, right. So this is a point group which is called 2 by m 2 by m 2 by m. Or in other words, if I have two m's, right, a third two-fold axis is guaranteed, right. So if I have two m's here, there should be a two-fold axis of symmetry here. If I have these two m's, there should be a two-fold axis of symmetry here. If I have you know, these two m's, there should be a two-fold axis of symmetry here. So instead of saying 2 by m 2 by m 2 by m, I can just say that my point group is now m m m, right, with the two folds just being guaranteed. Okay. So now m m m has many you know, so if I list out the number of elements, I have 1, right. But I am saying that I have you know, so m m m is the same as 2 by m 2 by m 2 by m. This is a short form notation. Okay. Now if there is 2 by m, I said if I have any axis, any rotation axis which is cut by a mirror, I get inversion for free. That is proven already. Then I have a two-fold axis about 0 0 0 1, I have two-fold about 0 1 0, I have two-fold about 1 0 0. Similarly, I have mirrors about 0 1 0, I have mirror about 1 0 0, I have mirror about 0 0 1. Okay. So my MMM point group now, right. So MMM is a group, it contains group of all these symmetry operations, it has an H equal to 8, right. So, in an orthorhombic crystal system, I started with the first point group is 2 2 2, the second point group I said is M2 or 2 or M2M, right. So, these are all one and the same, and the third point group is the MMM, right. So, which has more symmetry elements, and in fact, it encompasses all the symmetry elements that are there in 2 2 2 and MM2, right, and this is my holohedral point group. Then if I ask the question which of these point groups has an inversion symmetry, right. So, the 1 bar symmetry, right. So, which of these point groups, which of the orthorhombic point groups is centrosymmetric, if I ask that question, then the answer is so I have MMM has the 1 bar, right, in addition to other elements. So, MMM is a centrosymmetric point group, or in other words, any point group that contains 1 bar, 1 bar is the inversion operation, right, is said to be centrosymmetric. Right. In other words, if I do not have 1 bar, it is not centrosymmetric, right. So, for example, something like MM2 is not centrosymmetric. Okay. Something like 2 2 2 is not centrosymmetric, something like 2 is not centrosymmetric, right. Something like M is not centrosymmetric, something like 2 by M, however, is centrosymmetric. Okay. Okay. So, let us stop here. We have looked at 3 different crystal systems, and tomorrow we will in the next class we will just list out all the other crystal systems and then write down all the 32 different point groups that come as a result of what we are doing here. Okay. So, we will start with orthorhombic crystal system, we will look at the stereograms of this, and then we will proceed to more tetragonal, cubic, and so on and so forth. And as you keep on increasingly going more towards the cubic system, the number of symmetry elements keep increasing, right. So, it becomes hard to keep track of them. As of now, the highest number of symmetry elements I wrote are 8, right. But you go to cubic systems, it becomes so the number of symmetry operations becomes much larger, 64s and so on and so forth, right. So, we will see how to elegantly look at all these symmetry operations through what are called stereograms, right. So, in the next class we will do that. Okay, thank you very much.